Hi, my name is Solomon, and I am the ROS engineer here at Interbotix. Today, I will walk you through working with our ARM Vision Kit. First, make sure that you have a computer or laptop that is running Ubuntu Linux and ROS. Also make sure that you have installed our ARM Interbotix ROS packages. As far as hardware goes, make sure that your ARM is connected to your laptop or computer over a micro USB cable, and that you have a 12-volt power source plugged into the ARM. Also make sure that you have a camera and its stand, that you have the camera on its stand and that it is facing towards your tabletop surface. Make sure that the camera is plugged into your computer using a USB 3 cable and it is plugged into a USB 3 port. Now open up a terminal on your laptop or computer by typing Ctrl-Alt-T. Then type ROS launch Interbotix XSARM perception XSARM perception.launch robot model is equal to WX200. In this case, I'm using the Widow X200 ARM, but if you are using a different model ARM, you would stick the model name here. Use ArmTag Tuner GUI is equal to true. This will open up a graphical user interface that will allow you to figure out where the position of the arm is with respect to the camera. And also type use PointCloud Tuner GUI is equal to true. This will open up a graphical user interface that will allow you to tune some parameters for processing the raw point cloud that is obtained by the camera. Then hit enter. All right, so here we have the ArmTag Tuner GUI, the PointCloud Tuner GUI, and Rviz. Let's just do some configuring to Rviz here. All right, so we can see that the objects are within the camera's field of view, so that's good. Now what we're going to do is torque off the arm and then manually manipulate it so that the AR tag that is on the end effector is in full view of the camera. Then it will torque the arm back on. So open up your terminal, press Ctrl-Shift-T to open up a tab, and type ROS service call Widow X200 torque enable group arm false. If you are using a different model arm, you might have to put in the model of the arm. Instead of putting Widow X200 torque enable, you would put in the model name torque enable. Then we're going to prime it so that when we actually manipulate the arm, all we have to do is press enter. Okay, now let's bring up the ArmTag Tuner GUI. So you'll see a field called num samples. This can range from 1 to 10. For maximum accuracy, we're just going to raise it up to 10. What this will do is when you press the snap pose button, 10 different snapshots of the AR tag will be taken by the camera. The April tag algorithm will then run 10 different times and probably come up with slightly different poses for where the AR tag is with respect to the camera. What my program does behind the scenes is then averages all those poses together to hopefully come up with a pose that is more accurate. So let's click Snap Pose, and here we go. Look at the description in the GUI. It says, snapped pose represents the transform from the camera color optical frame to the Widow X200 baselink frame. So the camera color optical frame is over here. Let's just go and see where that is specifically. So camera color optical frame is here. So this transform is published with respect to the Widow X200 baselink frame you can see over there. Awesome. Something to note is that this pose will be saved to a YAML file called statictransforms.yaml after ROS is shut down. This file is located in the config directory in the Interbotix XSARM perception ROS package. You only have to do this step once if you're never going to move your arm or camera from where it is currently set up. If you do move the arm or camera, you will have to run this calibration procedure again. Now, let us torque off the arm and put it back into its sleep position. Go back to the terminal, click the up arrow key twice so that you have group arm false there, and then while holding the arm, click enter on your keyboard. Then torque the group on so that when you actually run the demo later on, the arm will actually move. It is also possible to do perception on our LoCoBot platforms. Let's talk about hardware setup. One way to do this is to have a keyboard, mouse, and monitor directly connected to the computer on the LoCoBot. Another approach, which is the approach I'm going to use, is to have a remote computer or laptop connected to the LoCoBot computer over a Wi-Fi network. In this case, your personal remote computer should have Ubuntu Linux and ROS installed. Also, it should have the remote software packages installed as well. Two other things to note is that the ROS master URI variable in your remote computer's bashrc file should be set to the computer name of the LoCoBot computer, which is usually LoCoBot. Another thing is that your personal computer and the LoCoBot computer should be connected to the same network. So open up a terminal by pressing Ctrl-Alt-T and SSH into the LoCoBot by typing SSH-X LoCoBot at locoboti.local. The -X flag allows us to do window forwarding. This allows us to start up graphical user interfaces on the LoCoBot, but have them display on your remote computer. Also, I'm using LoCoBot I in this case. We have lots of LoCoBots in our office, and in order to make sure I'm SSHing into the right one, I changed temporarily the LoCoBot I'm using to have a computer hostname of LoCoBot I. But in your case, you will always have a LoCoBot computer that's called LoCoBot, so you should always SSH by using LoCoBot at locobot.local. So press enter, type yes, the default password is LoCoBot, and you should be in. Now let's start up the perception launch file by typing ROS launch Interbotix XS LoCoBot perception XS LoCoBot perception.launch robot model is equal to LoCoBot WX200. I'm using a LoCoBot platform with a Widow X200 ARM, but if you're using a different model of LoCoBot, you should put the model name over there. Then I'm going to type use Rviz is equal to false. When you're working on a remote computer over a Wi-Fi network, you do not want to have Rviz taking up all the bandwidth. It's just going to lag like crazy. Instead, you're going to want to load up Rviz on your personal computer directly. So we're going to set this to false, since we don't want Rviz running on the LoCoBot computer. And now the next three commands that I'm going to type are completely optional. I'll discuss more about them in depth once after I finish typing them out. Use ArmTag is equal to true. Use ArmTag Tuner GUI is equal to true. And use static transform pub is equal to true. By default, all of these three parameters are false. And the reason for that is you don't really need them. As you might know from the standalone ARM Vision kits that we did a tutorial on, the ArmTag related nodes are there so that you can figure out where the arm is with respect to the camera. In the case of the LoCoBots, though, we already have a URDF that defines this, so we don't really need to do calibration. The only reason you'd want to do it is if maybe you want to get some better accuracy, finding out what the pose is of the AR tag with the camera directly, because there could be some error when it comes to the actual build of the physical LoCoBot, or maybe the AR tag is placed slightly off center on the AR tag plate. In general, I haven't found this to be so much of an issue. You know, whether or not you did calibration, the arm was still able to pick up the little square cubes that we have. So in general, I recommend not to set these parameters to true, but they are there if you want to use them. And for this tutorial, I am going to use them just so you understand how they work. Finally, the last launch file argument you want to set is use PointCloud Tuner GUI is equal to true, and that parameter just allows you to have a GUI that comes up to tune different filter parameters. Now press enter, and here is the PointCloud Tuner GUI and the ArmTag Tuner GUI. Now in the terminal, press Ctrl-Shift-T to open up another tab with a terminal. Keep in mind that this terminal now is actually on my personal computer, whereas the first terminal is the one that's SSH into the LoCoBot. So on your personal computer terminal, we're going to launch Rviz by typing ROS launch Interbotix XS LoCoBot descriptions remote view.launch Rviz frame is equal to LoCoBot base footprint. We're not doing any navigation here, so we're going to set the fixed frame to be the base footprint of the LoCoBot. Now press enter, and Rviz should start up. Here we go. Let's just do a little bit of configuring. Exit that. Set the camera display to true. We don't want to see the raw point cloud. Let's also set the perception displays to true, and we should see a live view of the point cloud. Filtered point cloud data, resize this. Great. So it looks like our camera has a good view of our small cubes. So now what we're going to do is torque off the arm, which is by default torqued on. Move it so that the AR tag is in view of the camera, torque the arm back on, and go from there. So go to your terminal again, press Ctrl-Shift-T to open up another tab. In this tab, whether it's on the LoCoBot itself or on your actual remote computer laptop, it doesn't matter. You can do the same command anyway. Raw service call LoCoBot torque enable group arm false. Press enter, and we're going to prime the next command to say true so that when we actually move the arm, all we have to do is hit enter on the keyboard. All right, so here we go. And now you should be able to see the AR tag in the field of view of the camera. I'm going to press enter. And let's bring up the ArmTag Tuner GUI. And just like we saw before, we're going to set this up to 10. And let us focus on the transform that is going to be published. In this case, it's the transform from the LoCoBot base link frame to the LoCoBot plate link frame. So let me show you where those frames are. Base link is here, and plate link let's also change the alpha on the robot model to be something like 0.5 so you can get a better view of that. Okay. So now when I press the snap pose button, you should see this transform shift a bit. This is the default transform defined in the URDF. And now let's see what the camera tells us. Okay, so it looks like it's saying that we were off by 1 millimeter in the X direction, about 4 millimeters in the Y direction, because by default, these are both 0 in the URDF. And then Z, I think by default, it's about 8 point something centimeters. So we're off by a little under a centimeter, or about a centimeter in this case. So the X and Y error could just be due to how you placed the AR tag on the arm's end effector. Maybe you didn't cut out the AR tag so that it's completely center, or when you actually taped it on, it was a little bit off center. So those could be issues. And also physical build, like I said before, could also attribute that. Okay, so once you have this pose, when ROS is shut down again, it is saved to the static transforms.yaml file, like I explained in while setting up the standalone arms. So you never have to do this step again. if you want to load this custom transform to the URD to the TF tree when you're actually working with the LoCoBot, make sure to set use static transform pub in the terminal to true. But there's no need to set use ArmTag or use ArmTag Tuner GUI again to true. You could just leave those to be false at their defaults. And if you don't want to load the this calibrated pose to the TF tree when you want to work with the physical robot, you could just leave the use static transform pub to be false, and it'll just use the transform defined in the URDF. Okay. As far as actually tuning the filter parameters, we're going to explain that. I'm going to explain that right after this. And it works, it's the same way for both the LoCoBot or for the standalone ARM. Now let's bring up the PointCloud Tuner GUI. So the raw point cloud that is obtained from the camera goes through all of these filters sequentially. It starts out with the crop box filter, then goes into the voxel grid filter, and then goes into the segmentation filter, etc., and etc. So before we start with the crop box filter, let's just change the frame of reference here. So instead of camera color optical frame, we're going to be using the camera depth optical frame. Okay. So now that we see where the frame of reference for the point cloud data, let's talk about the crop box filter. So the green semi-transparent box that you see is represented by the limits in these 6 fields. When it comes to getting the point cloud data that we only want to be able to see the tabletop surface and the small objects on the surface. We do not want to see, in this case, like part of the arm. So let's cut the arm out of the point cloud. All right, so that's one side. Let's do this side as well, the Y min, Y max. We can also lower the height. Here we go. And Z max. All right. So the benefit of cropping out as much of the point cloud that you do not need is so that there's fewer points later to be passed on to the filters below. This will make the program run faster. Now let's move on to the voxel grid filter. So what is a voxel? A voxel you can think of as a small cube with the dimensions shown in leaf size, in this case 4 millimeters. So we have a 4 by 4 by 4 millimeter cube. Think of this crop box marker here as being filled with many of these small cubes. Any of the point cloud data, any points in the point cloud that fall within a given voxel will then be averaged into just one point or voxel. So the benefit of doing this is you further reduce the amount of points that are within your point cloud. So if I set this very low, so then my voxel size is very small, and as a result, I have a lot of point cloud data that is coming through to the next filter. As a result, also, the data will be, the algorithm will run a little bit slower. But if I raise this number, so then my point cloud becomes extremely sparse, and it might actually be less accurate since I have less data. So I've always found that 4 millimeters seems to do the trick. Okay. So as an FYI, this filter point cloud display shows the output of the voxel grid filter and the crop box filter. When it comes to the segmentation filter, we're going to have to uncheck this display and check the object point cloud display. This object point cloud display shows the output after running it through the crop box filter, voxel grid filter, segmentation filter, and the radius outlier removal filter. Okay. So what does the segmentation filter do? It's essentially responsible for cropping out the plane that the objects are on from the point cloud. So first off, it has to come up with a mathematical model for where the plane is in the point cloud. And max iteration sets the number of optimization steps, I believe, that is responsible for this. 50 is the default, but even if you raise it or lower it, I didn't really see it to have too much of an effect. Anyway, after creating a mathematical model for where the plane is located, you can set the distance threshold. This is the meters perpendicular to the plane, where if data falls within there, you want to be cropped. You want to be considered part of the plane and cropped out. So in this case, I'm saying any data that falls within plus or minus 5 millimeters from the mathematical model of the plane should be cropped out. If this value is too small, like here, then you're going to start to see part of the plane. But if it's too large, you're going to start cropping out your object, so that's not good either. So ideally, you want to raise this value until you stop seeing the plane being cropped out. So something like 5 millimeters seems to work just fine. Let's just zoom in here a bit to see the points better. All right, so then we have the radius outlier removal filter. This is just a filter so that in case your environment has a lot of noise, or maybe your camera that you're using has a lot of noise, you can crop that out here. So what these parameters mean is you're essentially saying for any given point in the point cloud, I want you to search within a 1 centimeter radius. And if I'm able to find 5 other points within that radius, you should keep that point. Otherwise, throw the point out. So if you want to reduce noise, you can either increase the minimum neighbors or decrease the radius search. But let's say you are starting to crop out too much data, then you can lower the number of min neighbors or increase the radius search as well. All right, so now at this point, we should just have a point cloud that's showing the objects. So what we have to do now is figure out how many clusters are there in the remaining point cloud. And that's where the cluster filter comes in. First of all, what is a cluster? We're defining a cluster that as any point that is within a group of points such that any point is within a certain tolerance of another point. In this case, I've set it to be 2 centimeters. So just for example, like this point over here is within 2 centimeters of this point over here. So that's going to be considered part of the same cluster. But a point here and a point over here is definitely further away than 2 centimeters. So they will be considered part of 2 independent clusters. Something else to think about also is that these spherical markers represent the centroids of each of the clusters, both the XYZ position of the cluster as well as the average RGB value of the cluster. So then let's move on to the min size and max size. Min size means that even if you have a small group of points, you have to have at least 50 points in that cluster for it to be actually defined as a cluster. So this is good because let's say you do your best with removing noise from your radius outlier removal filter, but you still have some noise in the image. It's fine because as long as the number of points in that small noisy group is less than 50, then it'll be ignored anyway. On the flip side, let's say the place where you have your camera is an environment where you have this object and you can't get the object out of the field of view of the camera. So what you can do is set the max size parameter so that if the object has more than a certain number of points, you can consider that not to be considered a cluster at all. All right, so now let's talk about a few problems that might come up. Let's say you see something like this, where you have one spherical marker that's representing 2 independent objects. So this happens because the closest point here to here is, in this case, within 4.6 centimeters of each other. So the algorithm is seeing this as one cluster. So to fix that, all you got to do is lower the tolerance. On the flip side, you might see a situation arise where one object might be considered as 2 independent clusters. And this could happen if the tolerance is set too low. So by raising the tolerance, that should fix the issue. Another problem that can arise is if you see the spherical markers blinking. Usually what that means is that the min size is raised too high, and you should lower it until the spherical markers stop blinking. Another thing to think about If you set the voxel grid filter parameter leaf size to be really high, that means fewer points are being passed down to the remaining filters. As a result, you should really lower the min size and max size parameters as well, proportionally. Similarly, if you lower the voxel grid filter parameter, then more points will be passed through to the remaining filters, and you might have to decrease the min size and max size parameters proportionally as well. At this point, once you see that the spherical markers are not blinking and that you see the same number of spherical markers as there are clusters, you are good to go. So just click the Save Configs button, and you should save it to the default filterparams.yaml file name. You could also save it to a custom file name, but then you would have to change the launch file argument called filterparams to point to your new config file. So click Save, Replace, and that is it. Thank you for watching this tutorial, and we'll see you next time.